Hello everyone! On this channel I've been creating Godot shaders of all kinds, but there is one type I've ignored until now, so it's time to fix that. It's the shader type particles, and as the name suggests, we'll apply it to a GPU particles 3D node. So let's take a look at how we can create a simulation of insects flying around a light in the fog. Alright, I said that the particles shader type is the last one I haven't worked with yet, but that's not entirely true. Godot version 4.7 will introduce a new shader type, texture blit, which will be an implementation of so-called drawable textures. However, at the time of recording this video, Godot 4.7 is still in beta, so I'll cover this feature later. Alright, let's get to work. I'll create a new 3D scene and add a GPU Particles 3D node to it. So let's do it. Right-clicking the Scenes folder, create a new scene. It is a 3D scene and let's call it, for instance, Insects. Okay. And as I said, adding a child node of the type GPU Particles 3D. As we know from previous tutorials, this node displays a warning triangle until we add at least one draw pass and also a particle process material. So I'll find draw passes in the inspector. It is right here. And I'll insert a simple quad mesh, pass 1, quad mesh. Okay, to which I'll assign a basic material. So let's click it and find the material property and create a new shader material 3D. I mean standard material 3D, sorry about that. We'll use a shader material for the particles themselves. So if I click the material, we can see it is a standard material with all expected properties. Let's scroll up. And then we need to configure several basic parameters of this material, so we are ready to fine-tune the final effect. First of all, so I'll scroll down again, and first of all, we want these little squares, these, to resemble a swarm of insects more closely. So I'll reduce their size, and I think we can get rid of all these gizmos. So clicking the perspective, these three dots, and disabling gizmos and transform gizmos. Okay, that's much better. So let's set size to, as I said, to 0.4, for instance, 0.4. 0.4. That's better. Furthermore, we'll be changing their transparency based on the current position of each particle. So I'll set transparency to alpha. Okay. And for this change to actually take effect, I'll open vertex color and select use as albedo. Finally, as the last part of the basic setup, I'll change billboard mode, scrolling down to the billboard section and change the mode to particle billboard. So now we can see it faces the camera and always will face the camera no matter how I rotate the view. So that takes care of the basic draw pass. And now we need to set up the process material. So scrolling up this time and expanding the process material. And normally I would choose particle process material here, but this time we'll select shader material. Let's click it, for which we create a shader, which is actually the main topic of this tutorial. So click again, and to the shader property, let's create a new shader, and this time it's type shader mode particles, and it's called shaders insects.gd shader, and I'll put it to the shaders folder and create, and click again to open it in the shader editor. As we can see, the shader type particles uses different functions than other shaders. Instead of vertex and fragment, we have start and process. As the names suggest, the first function is called when a particle is spawned, and the second one is called every frame during its life cycle. This is how we'll control the movement of each particle so that together they produce the desired effect. And as usual, we'll begin with uniform parameters that will let us configure the final appearance of the effect. There will be 7 parameters in total. The first one will determine how strongly the particles are attracted to the light, which is typical behavior for some insects. So let's do it right here at the top. Uniform float. Attraction strands. Okay, with a hint range and the initial value 0.5, and the range goes from 0 to 1 with the step point 0,1. Next, we'll want to influence the amount of chaos in the swarm's overall movement, as well as their flight speed. So next to parameters, uniform float chaos with a hint range and again 0.5 as the default value, and again the range goes from 0 to 1 with the step point 0,1, and the third one uniform float speed with a hint range, and let's start at 1, and the range goes from 0 to, let's say, 2, again with the step point 0,1. The particles will fly in spherical paths around the center. So we'll define the minimum and the maximum radius of this orbit. So uniform float orbit min hint range, and let's start at 1, and this time we can make it from 0 to, let's say, 500, and the step, of course, with such a range can be just 1. All right, and I'll create the similar thing for the max uniform float orbit max with a hint range and 2. Okay, and again from 0 to 500, and the step just 1. All right, so we have 5 parameters defined, and let's add the final 2. And to prevent the particles from moving too regularly, we'll offset their flight using a parameter called flutter amplitude. Okay, uniform float flutter amplitude with a hint range, and 20 is the default value, and the range goes from 0 to 200, and this time 0.1 is okay for the step. All right, and the final parameter will define the distance from the center at which the particles will spawn. So uniform float spawn radius with a last hint range and the initial value 20. Okay, and the range goes from 0 to 200 with the step point 0,1. All right. No, sorry, I did it wrong. Let's do it again. So the default value is 1, and the range goes from 0 to 500. That is the step 1. Okay, this should be correct. That completes the parameters setup, and now I'll insert 2 helper functions that we know from previous tutorials and use as pseudo-random number generators. I'll just paste them so that I don't make any mistakes while retyping them. Okay, and let's expand this window so we can see all of that, and I'm pasting the mentioned functions. So as we can see, both functions return a number, float, in the range from 0 to 1, because the result is the result of the fract function. Okay, yep. And the first takes a float as its input parameter, while the second one takes a vector too, so hence the names #11 and #12. With that, all the preparation is complete and we can start writing the start function. Okay, so a particle system has one important characteristics. Particles are unaware of each other because all calculations happen on the GPU. So, if we don't want all particles to move along identical trajectories, we need some way to distinguish them. Fortunately, Godot provides us with the index variable, which contains the index of the currently spawned particle based on the configured total count. Thanks to this index, the hash11 and the hash12 functions will always produce different results. And since index is an integer, we'll convert it to a float and assign it to a variable called seed. So let's get to the start function and do this. Float seed equals float of index. Okay, perfect. Next, we want to configure various movement parameters for the particle, which we'll later use in the process function. Another built-in variable called custom is very useful for this purpose. It's a vector 4, so we can store up to 4 float values in it. The first of these will be the distance at which this particle orbits around the center. So we'll choose it from the configured range. Let's add the next line. Custom.x, the first component, equals mix of orbit min, orbit max, and the weight value is hash11, the pseudo-random number, seed times, and let's add some arbitrary number, 7.13. Okay. By the way, all of these and the following numbers are chosen randomly, and you can replace them with any others you like. Their only purpose is to increase the randomness factor. Then we want to know the speed and direction of movement. We'll store the result in the custom.y. So first float, let's call it SPD because speed is already a uniform parameter, and the mix, and let's make it from, for instance, 0.4 and 1.6, and again the weight factor is a pseudo-random number, hash11 seed times, and this time, for example, 3.17. All right, and the direction float there equals hash11 and seed times, for instance, 5.53. And actually we want just to determine if it goes one way or another. So we need a value a -1 or 1. So if this pseudo-random number is greater than 0.5, so this is a ternary operator, let's use 1, otherwise -1. Perfect. And finally we can assign the result to custom.y, and it's simply SPD times there. Great. In addition, we don't want all particles to spawn at the exact same position, so we'll calculate a random offset and store it in the z component. So custom.z equals, and again, mix of 2, 7, and the weight factor of hash11 seed times, and this time 17 but 31, for instance. Alright, now we'll use another trick and store additional parameters in the built-in velocity variable, which is a vector 3. Since we only care about the particle's actual velocity inside the process function, not the start one, for now we can use it to store random settings for flutter and chaos. So let's do it. Velocity equals vector 3, and I'll put every component to its own line. And the first one is hash11 seed times, let's say 23, and times tau, because we are working on a sphere. So this is the phase x of the flutter. Now I'll copy and paste to create something for the face y, and this time let's multiply by 31. And finally, the third line, hash11 seed times, for instance, 41, and let's give it some more. Oh, no. This is a scale multiplier, so we'll simply put it to some other range, let's say from 0.4 to 1, which means let's multiply by 0.6 and add the 0.4. Perfect. All that remains is to set the particle's initial position. We'll imagine it on a surface of a globe, so we want to generate a random latitude and longitude, as well as a distance from the center. So I'll add 3 new lines to the start function. Float spawn horizontal is hash1 2, because we'll be working with a vector this time, vec2 seed and 0, let's say, and let's multiply the result by tau, because again we are on the surface of a sphere. Okay, now we need the distance, so float spawn dist equals hash1 2 vec2 seed, and this time let's use 1 for the second component and times spawn radius. Okay, our parameter. And finally the vertical. So float spawn vertical equals, and open bracket, hash1 2 of vec2 seed and, for instance, 3, okay, minus 0.5 times tau. Let's imagine that as the latitude, right? Yeah, from the equator up and down, so from -5 to 5, and multiply by tau to follow the sphere surface. And finally, let's save it, we'll assign these values to the built-in transform variable. It's a 4x4 matrix where the first 3 vectors represent the particle scale, which we won't use in this tutorial. We are only interested in the 4th vector, which controls the translation, meaning the distance from the center. And to spawn particles on the surface of a sphere, we'll again use a combination of trigonometric functions like this. So let's finish the start function. Transform, and as I said, the last vector, and dot x, y, z, first 3 components, equals vector 3, and again I'll put it to separate lines. First one is cosine of spawn horizontal. Okay, and let's multiply it by cosine of spawn vertical and times spawn distance. All right. Now the second one, that would be sine spawn vertical times spawn dist. Okay, and the last one, I think I will just copy the first line without the comma and paste it here and change the first cosine to sine, and the second cosine is okay, spawn vertical, spawn dist. Yeah, this is perfect. Okay, and with that, the start function is finished. Here it is. In the 3D editor, if I switch back, okay, we can see some activity already, but without the process function, which is currently empty, the particles move according to the default values, which we need to change. So the rest of the code, which will control the actual movement of the particles, will be written inside the process function. Okay, I'll open the full window again, and let's scroll down to the process function. Okay, so this time we are not working with UV coordinates, so the usual beginning will be a bit shorter. Basically, we just create a time variable for animation. Float time equals time times speed. Okay, and now I'll assign the values transferred from the start function to variables with more suitable names. The important thing is that these values are unique for each particle, which together gives us some nice chaos. So let's do it. Float or bit radius we take from custom x, then float orbit speed is custom y, then float orbit start is custom z, I think. Is it? Yeah, correct. And finally, the last one is the flutter frequency. So float flutter frec is custom w. Okay, and now values from the velocity vector. So float phase x is velocity x, float phase y equals velocity y, and finally the scaling of the chaos factor float chaos scale equals velocity dot z. All right, in this function, we want to do two things. First, calculate the particle's new position and assign it to the transform matrix, which is essentially the foundation of the entire effect. And second, adjust the transparency using the alpha channel of the color variable. That's all. We won't need anything more, but we'll get there through a step-by-step calculation. First, we determine the target position of the current particle's orbital path, once again using the trigonometric functions. So let's do it here. Float angle horizontal equals orbit start plus orbit speed times time. Okay, and the vertical one, so float angle vertical equals orbit start, let's say times 0.7 plus orbit speed times time times 0.4. Okay, and let's define the target vector, the three-dimensional vector, so the coordinates in the space. Vec3 orbit target equals vec3, and again let's add three lines. The first one is cosine of angle horizontal. So it is very similar to calculation in the start function times cosine angle vertical times orbit radius. Okay, the second one, sine angle vertical times orbit radius, and let's make it a little bit distorted, so times 0.8. And the third line, I'll just copy the first one and paste it here without a comma. And as just like in the start function, I changed the first cosine to sine, angle horizontal times cosine angle vertical times orbit radius. Correct. Next, we want to enhance this position with random chaos, so we'll create a so-called flutter effect along all three axes. As you can see, as you will see, the calculation uses both uniform parameters and values obtained from the start function. So let's do it here. Float fx for flutter x, to make it shorter, is sine of time times flutter frec times 1 plus phase x times flutter amplitude, the uniform parameter, times chaos times chaos scale. Okay, you might be wondering why I am multiplying by 1 when it's not necessary. The reason is that we will have 3 very similar lines, and everything else will be nicely aligned vertically. Let me show you. So copying and pasting twice, and let's call it Fy and Fz. And now in the second line, I'm changing sine to cosine, and the multiplicator is 1.3, and we are using phase y, and everything else is the same, and the Fz line with sine of flutter frec times, this time, 0.7, and this time it is phase x plus phase y. Okay, and the rest is the same: flutter amplitude, chaos, and chaos scale. Okay, and finally, let's combine these two vectors. So the target vector called target equals orbit target plus vector 3 with its components fx, fy, fz. Okay. Now we need to calculate the particle's attraction toward the center. First, we determine the current position and the direction toward the calculated target. So let's do it here. Vec3 pose equals the transform variable, and again the last vector, and x, y, z components, and let's find the direction. So vec3 delta is target minus pose. All right, then we define a random strength of this attraction. Float strength equals mix of, and the range would be 0.01 and 0.18, and attraction strength is the uniform parameter and our weight factor. Okay, and finally, let's calculate the acceleration and use it to move the particle to its new position, which we assign to the transform matrix. So vec3 axle is delta vector times strength value times 60. So it's more pronounced. And finally, our position will change to position plus acceleration times internal delta times speed. Okay, and before I write the last line, we'll just switch back to see the 3D editor, because now we'll see some change finally. Let's assign the final position to the transform variable, and I'll just copy transform3.xyz and do it here. Equals pose. Okay, and here it goes. Let's just zoom out, and the result looks a bit better, I would say, and we can observe what happens if I go to the inspector and change the amount from 8 to, let's say, 100. All right, very interesting. Actually, I supposed it would be orbiting a little bit, so perhaps there is something not entirely correct. Let's find the parameters. Spawn radius. Okay, just give me a second, I'll find the problem. Okay, I found it, and I made a mistake in the start function where I defined a custom variable, because I mistakenly defined custom Z as custom W and completely omitted custom W. So please find the line with custom Z and change it to this value, #11 seed times 11 dot 17 times tau, and then custom W is the mix of 2, 7, and #11 seed times 1731. And now you should see this kind of chaos, and it really much more resembles the insects orbiting around a white source. Okay, so now when we change the other parameters, we can achieve different variations of this effect. So let's find it in the inspector again. And for example, let's just zoom out a little bit. I'll change the attraction strength. So now it's not being attracted at all, or maybe it is completely the opposite. Okay, let's keep the 0.5 value. We can increase the chaos. This is definitely have some effect, or decrease it. Let's change the speed. Now it's much faster. Now it's much slower. Okay, the orbit can be of course changed. It's too much maybe. And the flutter amplitude, if we want the insect to flutter a lot more or less. Okay, and spawn radius, which determines how far from the center the particles will spawn and then attracted to the center. So yeah, let's get back. Very well. All that remains is to add alpha channel changes based on the particle's position. We'll do it like this. So I'll just expand this again and go to the end of the process function and add these lines. Float proximity alpha is 1 minus clamp of length position divided by orbit max. Okay, and the range is from 0 to 0.6, so we get it somewhat more transparent if they are farther from the camera, and the color A is mix times 0.25, 1, and the value proximity alpha. Okay, let's take a look. All right, I think it might be a bit dimmer. And actually, this is important. Let's find the material again. And since we set vertex color uses albedo to on, it is actually affected by this variable color. If I turn it off, it's definitely not. Now we have a solid white, and this assures that we can influence it in the shader code, by the shader code. Okay, so as I said, the result may not look dramatically different, but once we add more objects to the scene, this improvement might stand out more. Let's try it. So what are we going to need? First of all, a light source around which the swarm will orbit. I think that the OmniLight 3D node is perfect for this, so I'll add one to the scene with the following parameters. So right-clicking the root node, add child node, and OmniLight 3D. I have it here. All right. And I think we need to change some parameters for it. So let's expand the light and no, first the Omni, and I think it should have a bigger range. So let's go set 15 and change the color to something like dark yellow. Okay, something like this. And the energy should be definitely bigger, so let's increase it. And now we can see that some of the particles get the yellow tint. Actually, we don't see the light source itself because the light is not visible as it is. It only reflects from something, so we'll get to that. All right, and we need one more thing. Volumetric fog energy increased as well. It doesn't have any effect now because there is no fog around us, but once we add it to the world environment, we'll see how important this parameter is. Okay, by the way, if anyone doesn't want to build the scene manually, you can find it already prepared in the Godot Shader Pack product, which I added, where I added this entire project. All right, so as I said, we can see some illuminated particles that are close to the source, but it would be better to emphasize the light source itself, because a light source is not directly visible on its own, as I said, it only reflects off the surfaces of other objects. So I'll add a mesh instance 3D and set it up as a sphere with these parameters. So right click in the root node, add child node, mesh instance 3D. Okay, in the inspector, let's change it to sphere mesh, click it, and now the radius I'll set to 5, height to 10, now it's a bigger sphere, and it would be nice if it emits some color. So let's scroll down and edit a new standard material 3D, click it again, and I'll find emission, set it on, and in the emission, we'll change the color to something similar to what we already have. So how we mix the yellow here? Yeah, no, something like this. Okay, and it could shine a bit more. Let's increase the energy multiplier to 6. Now that's better. Okay, we could actually add a normal map with some noise texture to simulate some irregularities on the surface, but I think it won't be too visible anyway, so let's skip this part. And now it looks almost like a street lamp, especially if we add a pole for it to be attached to. This time it will be another mesh instance 3D configured as a cylinder. So again, I'll right click and you know what, let's rename this one to bulb, for example, and adding another mesh instance 3D, which I call pole. Okay, and in the inspector, the mesh is cylinder mesh. Click it again, and now the top and bottom radius will be increased to 2, and the height to, for example, 45 meters. And of course, we need to shift it all, across the y-axis. So let's expand the transform position and set the position y to -25. That's better. Okay. And if we wanted to run the scene right now, we wouldn't see anything without a camera. So I'll add one along with a directional light 3D to make the object stand out a bit more. Right-clicking the root node again, adding a child node, camera 3D. And now we can see something in the preview, but the camera is currently in the origin. We want to shift it a little bit. So I'll find the transform again and set the position Z to, let's say, 50. Okay, that's better. All right, and as for the directional light 3D, right-clicking again, add child node, directional light 3D. Now we can see that the pole is better visible because it's illuminated by this light source. And let's find the light property, and this is important. Let's cancel the volumetric fog energy. Let's set it to 0, because otherwise this light would illuminate the fog, which is still not there, too, and we definitely don't want that. And let's just move it a little bit along the z-axis. It's not entirely necessary, but it might be better if we take a look at the whole scene and we don't see any gizmos because I turned them off. Let's turn them back again. View gizmos, transform gizmo. Now we can see the light source right here. And the last thing, I think we could rotate it a little bit so it's not illuminated exactly from the front, like this and this. Yeah, sure. Why not? Let's keep it like this. Okay, but the environment could still use some more improvement. If we start the scene? Yeah, now we can see it, and we can see that the gray background is definitely not too impressive. Let's fix that. So I'll add the last child node called world environment. Open it in the inspector, create a new environment, click it again, and change the background to custom color. Okay, that's better. And it would look even better if a nice glow formed around the light source. And to achieve that, we are finally getting to the volumetric fog. Let's enable it, and that's everything. Can you see the halo? It's pretty cool. And if I start the scene, yeah, I think we achieved almost the same effect as we had at the beginning of this video. And of course, if the particles don't seem visible enough, let's get out of that, we can improve their material. For example, I'll give them a green emission color and increase the energy. So let's select GPU particles 3D again, and we have selected the material in the first draw pass. And as I said, it should emit some color. So turning on the emission, and let's change the color to green and increase the multiplier. Now we can see something, and if I start a scene, we should definitely see it more prominent. Yeah, it looks pretty cool. Okay, and with that, I think we are completely finished. Thank you very much for watching. Obviously, this scene is still quite imperfect, and in a real game we would probably create a much better looking lamp and additional models in Blender or another 3D modeling tool. We could also replace the quad mesh with a different object or even an animated sprite, which could simulate flapping wings. But those are all details that everyone can experiment with on their own. For now, take care, good luck with your projects, and I'll see you in the next video.